In my video lecture on the Mos capacitor, we have discussed the various cases of the Mos capacitor, that is the energy band diagram of Mos capacitor in the accumulation, inversion, and the depletion regions. And what we have concluded is for the MOSFET to enter into the inversion mode, the surface potential must be equal to twice the Fermi potential, which is, that is this phi s, that is the bending of the bands at the surface, should be equal to two times Q of 5, where Q of 5 is the energy difference between the Fermi level and the intrinsic level of any material. Because if Q of 5 denotes the amount by which EI is above EF, then EI should bend by the same amount below EF in order to invert the channel, or in order to induce the channel, or to invert the substrate. That means if we have a substrate which is p-type, we are inverting it with which is we are creating an n-type material from a p-type substrate just upon the application of the applied voltage. Now, a very important concept which remains in the Mos capacitor is the threshold voltage. We do not have to do these equations. We are doing away with these equations because these are beyond the scope of your semester. But before I take up that threshold voltage with you, I just want to discuss this graph, that is figure 614, which most of you have requested for me to discuss, is the charge versus phi s, that is the surface potential. Now, what we are doing here is phi s is the bending of the surface. When phi s is equivalent to 0, that means EI is at its equilibrium position. When phi s is positive, it means EI is below EF, and when phi s is negative, it means EI is above EF. So it's it's the opposite. We are taking positive along the top side and negative along the we are taking negative along the top side and we are taking positive along the bottom side. Yeah. Now this is the phi s which we are plotting here. That is phi s 0, negative along this side, positive along this side. Now it says when phi is, that a surface potential is 0, we're not sure what will happen, but when the surface potential is negative, that means when the bands are bending upwards. That is what I told you, that is phi of s is negative, means this equilibrium, because phi s measures the equilibrium position of, or it measures the amount of bending of EI below EF. When EI is above EF and is bending upwards, that means when it is negative, we have the p-type substrate. So this is shown by the charge, that is Qs in coulombs per unit area, that is coulombs per centimeter square. So when phi s is negative, the holes are in greater population, the MOSFET or the Mos capacitor is in the accumulation mode. So that is what it is showing. When phi s has a greater magnitude, then obviously the population of holes is much more. But when the magnitude decreases and it reaches to 0, the accumulation decreases and holes decreases. So this is in consistency with the energy band diagram, which means when phi s is more positive, the bands are bending towards the top, whereas when the value of when the bands are coming near to EF, or they are just reaching the position of EI, or they're going below this position, phi s becomes less negative. So, and then when it is 0, so the accumulation is decreasing. When phi s starts getting positive, that means when EI is starting to come below EF, or when EI is starting to shift down or bend down from its equilibrium position, that is when phi s is becoming negative. What is happening? Depletion takes place here, because EI lesser than EF means an n-type material. So as EI is bending below EF, or it is coming near to EF, it means the population of holes is decreasing and that of the electrons is increasing. So this is what is shown in this graph as, first there is the onset of the depletion like this, then we have the weak inversion where the population of electrons is increasing, but when phi s increases sufficiently and becomes twice phi f. So you can see if 0.4 is the value here, it means at least this population should be obtained, that is the quantity or the number of holes per unit area which we are obtaining at phi f equals to 0.4 must be obtained for a value of phi s equals to 0.8. Alright, and when we have phi s equals to 0.8, the population of the electrons increases abruptly, and this is what is known as the strong inversion. Strong inversion, it occurs when this EI has bent down below EF by the same amount by which EI is above EF. So that is the total surface potential must be equal to twice Q phi F for the inversion to take place. I hope this figure 614 is now clear to you. We'll just do away with these exponential expressions, whereas if you want to just go into their details, you can follow the solid state electronics book by Donald Deneyman. Yeah, it's just given there. And then now another one is the threshold voltage. Let's just take a look at here. We have here a Mos capacitor where we are saying that we deposit one type of charge on the metal and the equal and opposite amount of charge gets induced in the semiconductor. So if we are depositing a positive charge on the metal, it will look like this because we are plotting charge density versus the distance. So it's this one, maybe a spike of charge denoted by Qm. And on the other hand, towards the substrate side or the semiconductor side, we'll have the inversion charge density denoted by Qn, and below that we'll have the depletion charge. So it appears in a MOSFET that at the interface we'll always have the inversion charge, and below the inversion charge we'll always have the depletion charge. Now we have the Now the charge on the metal deposited on the metal has to be balanced by the charge on the semiconductor, which is equivalent to the charge in the depletion region plus the charge in the inversion region. So the charge in the depletion region is Q, Na is the accepted doping of the substrate, W is the width of the depletion region, minus Qn, that is the charge in the inversion. Why minus? Because we are dealing with the electron, so that's why it's negative. Yeah. And then obviously, Vi is the voltage which appears across the insulator. We know that Q is equivalent to C into V. V is equivalent to Q by C. So what is Qs? Qs is the charge which is in the semiconductor. Yeah, and here we are given with the expression of the depletion width. It's same for a PN junction. So just forget about it. Let's only take into consideration W. Now here the charge per unit area in the depletion region QD at strong inversion is given by minus Q Na into W M. So the expression is like this. Now the applied voltage which we apply on the metal gate should mirror this charge, because any charge which is present in the semiconductor must be balanced by the charge which we are applying on the gate, or vice versa. So threshold voltage is equivalent to minus Q by Ci, but this Qd is the depletion charge plus 2 phi f. But now why this 2 phi f? Because the voltage which we are applying on the gate must be sufficient enough to induce the strong inversion. So 2 phi f is a condition which is required for the strong inversion. Now this is for the ideal. This is for an ideal MOSFET, that is the threshold voltage will be equivalent to this expression which is given by the equation 633. Then we'll take up first the effect of real surfaces on the threshold voltage, and then we'll discuss the capacitance. Let's scroll down to that page. So then in section 6.4.3 we have the effect of real surfaces on the threshold voltage. So firstly, when we are making the metal oxide in a semiconductor capacitor or a MOSFET device, the metal may have one work function and the semiconductor, which is of which may be either of the p type or the n type, may have some another work function. So obviously, in as we are assuming in the ideal case that there is no work function difference, there will be a work function difference. So first of all, the applied voltage on the gate has to balance this, has to supply this amount of the work function difference between the metal and the semiconductor. So this term, which is phi ms, the term which is phi ms, that is the work function difference of the metal and the semiconductor, must be supplied by the applied voltage on the gate. Then only we'll be able to achieve the equilibrium diagram. Yeah. Mm. So we can even see in this very second para of the work function difference, if we try to construct an equilibrium diagram with phi ms is negative, we find an aligning EF. We must include a tilt in the oxide conduction band. Thus, the metal is positively charged and the semiconductor is negatively charged to accommodate the work function. As a result, the bands bend down near the surface, and in fact, you can just read out these details yourself. So, you must understand that in order to get a flat band, which means that the Fermi levels must be aligned, the two work function, the difference of the two work functions has to be supplied by the external voltage, because obviously the work function is measured as the amount of energy from the Fermi level to the vacuum level. So obviously it has to be balanced by the applied voltage. Then only we'll get a single Fermi level. And we have to include a tilt either on the metal side or on the semiconductor side, wherever we are, increasing or decreasing the work function. Then second thing is the interface charge. We have till now not included any interface charge in the threshold voltage equation, but in reality there may be some of the metal ions which may be present near the interface. For example, the alkali metal ions, particularly sodium, which is a positive, which is a single positive, it may be incorporated inadvertently in the oxide during growth or subsequent. I mean, this interface charge is that charge which may be present in near the oxide interface when the MOSFET is being fabricated, and it's just impossible for any designer to revert the design. Yeah, and we cannot do away with this. These are there, so we have to take the effect of these ions into our own equation so that we are able to get the exact measurements or the exact values of the charge or the voltages and so on. So that's the interface charge. Interface charge may be particularly designated by or denoted by QIT. You can read out the details here. So these are actually the these are actually the charges, interface charges, which are present near the silicon and silicon dioxide, or whatever may be the oxide layer, between the oxide layer and the silicon dioxide. So that is the interface trap charge, and it always is positive, so it needs a negative. So it induces a negative charge into the semiconductor. And then we have another charge. One moment. Yeah. Yeah. So we can have oxide trap charge, the charge which is trapped in the oxide, that is in the thickness of the oxide, denoted by QOT. We may have oxide fixed charge, denoted by QF. These are just like the charges which are wandering in the oxide, unwanted charges which are present in the oxide, and we do not know about it, but then we have to take it into account, because all these charges have to be balanced by the threshold voltage which we are supplying at the external gate. And then we may have the interface trap charge. Okay, so everything is given, all the details are given in this very para. You can just go through it and you can just read it out. So just as it says that in addition to oxide charges, we have positive charges arising from the interface states at the silicon dioxide interface. These charges are Qi, Then again, near the interface is a transition layer containing fixed charges QF. Transition is when the device goes from abruptly from the silicon dioxide into silicon. So while the silicon dioxide layer is being while we're reaching to the end of the silicon dioxide layer, the silicon does not immediately start, whereas it oxidizes. Some portion of it also oxidizes and it forms silicon OX. That means it can be its value can be SiO2, or it can be SiO3, or it can be even SiO. It may contain fixed charges. So then again, we are including all the interface charge by the term Qi, and it's like this one. And these will affect first the flat band voltage, that is the voltage which we want in order to achieve a flat band or a straightened Fermi level. And then in total we'll get the threshold voltage as, now earlier the expression was only QD by Ci plus 25, that is the depletion charge and the amount of energy required to achieve the strong inversion. But now we know that we need to have a work function difference in order to achieve the flat band voltage. So these first two terms are basically the flat band voltage. So that is this, and the interface charge density, that is Qi divided by Ci. Now here comes graph figure number 617, which shows that phi ms, which is the work function difference between the metal and the semiconductor, for an N plus poly N silicon or an N plus poly P silicon. That means when the gate is N poly and the substrate is N type, and when the gate is N poly and the substrate is P type. And along this side we have the doping concentration, whether it is the acceptor doping or it is the donor doping. Yeah. So N, when the gate is N and the substrate is P, the work function difference will always be negative and it will be more than 0.6. Yeah. So, and when we increase the doping, this difference is going to decrease. Similarly, when the gate is N plus poly and the substrate is also N silicon, then obviously the difference between the two work functions will be less as compared to that having a p-type substrate, because p has a work function which is around 5 electron volts or 5.2 or 5.3, whereas n is a material which has a work function ranging from 4.1 to 4.65 or 4.5 and so on. So we can just measure out these differences and we can just see. But when we increase the doping, here for the N type of silicon also, the work function difference reduces and it reaches to 0. So that is all the essence of the graph. Now it depends upon, now if we want to calculate the threshold voltage, if we know what is the doping value, we can find out the exact work function difference between the two materials. Yeah, that's it. And then now see, threshold voltage work function difference will be negative. It shows figure 620, which shows the influence of material parameters, the threshold voltage equations. What will be the value? So the work function difference will always be negative, as is explained in the figure. Qi by Ci, that is the interface charge, will always be negative. Now Qd, that is the depletion charge by Ci, it will be positive for the N channel and negative for the P channel. Then 2 phi f, that is the Fermi potential, that is the surface potential actually. It will be positive for N channel and negative for P channel. All the explanations are given there. And then the threshold voltage. If you are taking the N channel, obviously the threshold voltage will be positive. If we are using a P channel, which means an N-type substrate, the threshold voltage will obviously be negative. And if we are increasing the doping concentration, the threshold voltage will increase for both the cases. So this is all about the threshold voltage.